Assalamualaikum and good day. We are from Group 5. In this video, we would like to present our lab report for experiment 3, which is major losses in pipe. So, before we start the presentation, I would like to introduce my team members. My name is Faisal as a leader, and my friend Muhammad Akmal Azizi bin Samsir and Muhammad Zulhilmi bin Samsir. Okay, we go to the next part. Okay, I will present the abstract part. For the overall view of this experiment is to determine pipe friction factor, this F. In laminar flow, F is only a function of the Reynolds number and is independent of the surface roughness of the pipe. In turbulent flow, friction factor depends on both Reynolds number and relative roughness of the pipe wall. In engineering problem, friction factor is usually determined by using Moody chart, can be determined the other method with Colebrook formula and Blasius formula. The friction factor is then used in the Darcy-Weisbach formula to calculate the fluid frictional loss in a pipe. Okay, we go to the next part. Okay, the objective of this experiment is to determine pipe friction factor. Next, introduction. Major losses or head losses, which are associated with frictional energy loss per length of pipe, depends on the flow velocity, pipe length, pipe diameter, and also a friction factor, which is based on the roughness of the pipe and whether the flow is in laminar or turbulent. We use the Darcy-Weisbach equation to determine the energy loss in a pipe flow. In this equation, friction factor is used to describe the friction loss in a pipe. In engineering problem, F usually is determined by using the Moody chart. The major losses, which is F, also can be estimated by using another method such as from Colebrook formula and Blasius formula. Okay, that's all from me. I will pass to my friend.
Hello, my name is Muhammad Zuhelmi and I'm from Group 5. So I will present the theory and methodology. But first we go to the theory. For the theory, for the turbulent pipe flow, excuse me. So generally in turbulent pipe flow, between the 2 points for the horizontal, which has constant internal diameter with no minor head loss accounted, whereby the total head loss major head same with the major head loss. The pressure loss P and major head loss could be determined experimentally using Bernoulli equation. And then where P is pressure loss between 2 points, F is coefficient of the pipe friction, L is the length of the pipe, D is the internal diameter of pipe, density of flowing medium, V squared is square of the speed of flowing medium, G is gravity constant, and HL is major head loss. So we go to the next slide. For the turbulent pipe flow, the type friction coefficient depend on the equivalent pipe goodness and Reynolds number. An example of the equivalent goodness based on the type of pipe are listed in the table 1. So this is the table 1. So Moody's chart in figure 2 summarize the relationship between RE, FE, and DI. So we go to the next slide. The speed of flowing medium can be calculated using the data of the internal pipe cross-sectional area flow rate, um, where V is speed of flowing medium, Q is flow rate of flowing medium, and D is internal diameter of pipe. For the turbulent flow in smooth pipe, the F for the Blasius formula valid for RE smaller than exponent to the 5 can be calculated as follows. So this is the equation. Meanwhile, for the Colebrook formula, the F in turbulent flow can be calculated using this equation. This equation is an implicit formula that must be negatively resolved. First, estimate the value of F and place it in formula, then calculate the initial approximation. This approximation is used in the equation to calculate a second approximation. If the estimate value is taken from the Moody chart, the initial approximation is generally sufficiently accurate and the values only differ after the third decimal place. The F in turbulent flow also could be determined using a Moody formula, and that is the formula. Alternatively, the values F can directly be obtained using a Moody chart. So the apparatus and radars is a rotameter, two-tube manometer, six-tube manometer, differential pressure sensor, digital display for pressure, pump switch, main switch, electronic pressure sensor, return hose, return valve, interchangeable measuring object, water tank, drain valve, pump, various measuring section, feeding hose, gate valve, and thermometer. We'll go to the procedure. Hi everyone. So the procedure is there is I think 13 procedure all. So the first is connect the feeding pipe and return hose to the test pipe section. Number 2 is connect the manometer tube at one of the tube manometer to the test pipe section. Number 3 is slowly open the gate valve until reading of rotameter or actual flow rate, which is QX, reach 2. And number 4, open the ventilation valve on top of the two-tube manometer, let the water overflow the system. Number 5 is slowly open the ventilation valve on the top of the two-tube manometer until the preset minimum reading of two-tube manometer. Number 6 is slowly open the gate valve until the level of water at 2 manometer of H1 reach the maximum while H2 at minimum. Number 7 is reduce the QX to 5 different values by adjusting or reducing the opening of the gate valve. And number 8 is transfer the manometer tube at the two-tube manometer to the differential pressure sensor. Number 9 is adjust the flow meter values as previous reading. Number 10 is recording the reading of differential pressure sensor. Number 11 is reduce the QX to 5 different values by adjusting or reducing the opening of the gate valve, same as the data before. Number 12 is change the feeding and return hose to another pipe section. And the last one, number 13, is repeat the same procedure for the other pipe. So I will pass this presentation to Akmal.
Assalamualaikum warahmatullahi wabarakatuh. My name is Akmal. This week we will discuss about major losses in pipe. This is our result for the experiment, our data from the experiment. In this experiment, we have three types of pipe. First one is galvanized steel pipe, second one is copper, and third one is PVC pipe. PVC pipe, we will use three different dimensions. First one is 16 by 1.8 millimeter. Second one is 20 by 1.5 millimeter, and last one is 32 by 1.9 millimeter. Okay. Firstly, we need to know the roughness of pipe for each type. We can search on Google based on the type. Okay, and we can calculate. Now we will compare the coefficient of friction F that we get from the Moody chart and compare it to the one that we get from formula of Blasius, Colbrook, and Moody. Here we calculate to get the F from the Moody chart. First of all, we need to know the viscosity by using the ratio. After that, after we get the viscosity, we can calculate the Q average of each part, and then from that we can calculate to get the velocity using the formula for Q over pi d squared. After we get the Q, the V, and the viscosity, we can calculate the RE, and then we calculate the epsilon over D from both value we can get the F on the Moody chart. Now we can calculate the friction using the Blasius, Colebrook and Moody. This one, this F is from Moody chart. Blasius formula is a straightforward one. We substitute the RE value from previous table, and then also Colebrook is quite straightforward, but we need to assume the F here. So we can see in the figure where firstly galvanized steel pipe, we assume that F approximately equal to 0.031, and the final answer we get F equal to 0.03033. Second one is we assume that F approximately approach to 0.0291, and the final answer is 0.0306. We can conclude that for galvanized steel pipe, the F, the friction, is approximately equal to 0.03. Same goes to copper pipe, PVC, 3 of the PVC pipe. Okay. On the Moody chart, we also just substitute the value. The value different is because of every calculation have different decimal point, so that's why we can see the roughly different between each of formula. Next, we need to run the part in ascending order based on their head losses, major head losses. Okay, to calculate the major head losses, the formula is friction times length over diameter times velocity of the fluid squared power of 2 over 2G, 2 times gravity. Okay. The F, we use the one that we get from the Moody chart, and the velocity we used from the previous table. As we can see, the least value of the head, the lowest value of the major head losses is from the PVC pipe with dimension 32 by 1.9 millimeter, and the highest one is PVC pipe dimension 20 by 1.5 millimeter. As we can see, from the calculation data, PVC pipe with dimension 32 by 1.9 millimeter is the least head loss compared to the other pipe. The factor that may affecting the value is velocity of the fluid, friction between fluid and the surface of the pipe, and the inlet pipe diameter. Head loss, major head loss is proportional to friction and velocity, but inversely proportional to diameter. Third one, and the factor that may contribute to error is one is a bubble, which can affect the pressure. Second one is the edge of the pipe may not be new or has been used for a while, meaning that if it is used pipe, the epsilon will be different. While taking the reading, our eyes may not perfectly parallel to reading, so that the reading will be much away. And also the temperature may affect the viscosity of the fluid. we can conclude that there are a few aspects that we need to consider in order to get the least head loss or error. The type of pipe is contributing less effect, not as much as the flow meter rate of the fluid and the diameter of the pipe, which affecting the friction and lowering the head loss. In this experiment, we can see that the PVC pipe with dimension of 32 in diameter by 1.9 mm in thickness has the least head loss with value of 0.023778 meter, with the lowest value in friction and the highest value in diameter. That's all from us. Thank you.